Good day, students. Welcome to this revision session. Today, I'm going to be looking at chemical equilibrium. I want to focus on a question that came in November 2002, paper 2, for this year was called 9701. The question was focusing on calculating the equilibrium constant Kc, given number of moles which were initially present, and then we're supposed to determine number of moles at equilibrium, concentration at equilibrium, and as a result, determine a numerical value for Kc. It was a question that was regarding the reaction between ethanoic acid and ethanol, okay, where we form the ester and water. So instead of ethanoic acid here, I'm just going to write acid, okay, acid plus alcohol, okay, then reversible sign here, and then I'm going to put here ester plus water, okay. Of course, the acid is going to be ethanoic acid, and the alcohol is going to be ethanol, okay. Our ester is going to be ethanoic, and we are going to have water. According to this question, the examiner for this particular year decided to give not moles, but to give masses of substances that were being mixed. For instance, in this question, it was saying 6 grams of the acid was mixed with 6 grams of the alcohol and 4.4 grams of ethyl ethanoate. Okay, in actual fact, you are mixing acid 6 grams, alcohol 6 grams, and 4.4 grams of ester, no water, and then the equilibrium mixture is allowed to come to a dynamic equilibrium. Dynamic equilibrium is when the rate of the forward reaction is now equal to the rate of the backward reaction. Okay, so the procedure that we use when we are calculating these questions is to look at what is available initially, what is available at equilibrium, concentration at equilibrium, and finally we can then determine a numerical value for Kc. So initially, okay, as indicated in the question, initially we have 6 grams of the acid, 6 grams of the ethanol, 4.4 grams of the ester, and obviously there's 0 for water. Okay, so we want to use this information to look at initially how many moles of each were present. Okay, given the mass, okay, of the acid, we can calculate the number of moles of the acid, okay, by saying number of moles is equal to mass given over the mR. So if you look at the mR for ethanoic acid is 60, all right? So we can say 6, okay? We can say here 6 over 60, okay? For the alcohol, if we calculate the mR for ethanol, we get 46. So we get 6 over 46. For our ester or ester, we can say 4.4 over 88. We want to change the information given to number of moles because these questions, they work with number of moles and that will help us to get our answer faster. Okay, so this is our calculations for the first part. Okay, so if you say 6 over 60, you're going to get 0.1. And then if you say 6 over 46, you're going to get 0.13. And if you say 4.4 over 88, you're going to get 0.05. Okay, and this one, 0, will not change. According to this question, it was found out that 0.04 moles of ethanoic acid was present at equilibrium. So this is initially. According to what we are given now, at equilibrium, okay, now we write equilibrium, okay, it was found out that 0.04, okay, this was given by the examiner, 0.04 was now present at equilibrium. What does this mean? You can actually see that the value has decreased from 0.1 to 0.04. So we should be in a position to determine what was the decrease, okay, from 0.1 to 0.4. Because this acid is being used, it's a reactant, so it's going to decrease. So on this side, you're going to experience decrease, and the decrease that we experience on this side, the corresponding increase will be reported on the other side. Okay, so if you do your mathematics there, you're going to find out that if we had 0.1 initially and we now have 0.04, the decrease being reported here is of 0.06. So it means we are supposed to subtract 0.06 from 0.13. So we have to do that. 0.013 minus 0.06. Okay, if we do that, we are going to get 0.07. Okay, so this becomes our number of moles at equilibrium for the acid, number of moles at equilibrium for the alcohol. But what we are decreasing here is going to be added on this side. So we don't subtract, we add. What we lost here, because the stoichiometry of the ethanoic acid and the ethanol is 1:1. So if we lose 0.06 here, 0.06 here, we are going to add 0.06 to this side. So we are going to say 0.06 and we'll get 0.11. Again, here we are going to add 0.06 and we get 0.06. We have done the first stage of our calculation. We now have number of moles of each of our reactants and number of moles of our products at equilibrium. Okay, so the final phase before we calculate is now concentration at equilibrium. Okay, concentration at equilibrium. The formula for concentration is number of moles over volume. Okay, this reaction vessel, we can actually call it V, its volume. So I could say here 0.04 over V, here 0.07 over V, 0.11 over V, 0.06 over V. Now, my values are now ready for calculating Kc. Okay, how do we express Kc? Okay, you should remember that when you are dealing with Kc, Kc is always concentration of products first, square brackets please, remember, alright, extra, okay, multiplied by H2O over reactants, acid, square brackets please, alcohol. Okay, that is very, very important because this means concentration. All you do is now to take the values that you have written above there. Okay, now we just want to substitute. Okay, so my Kc will be equal to 0.11. Okay, let me just do it more properly here. I'll use the usual brackets, 0.11 over V, okay, multiplied by 0.06 over V divided by 0.04 over V, okay, multiplied by 0.07 over V, okay. Now, if you analyze this question, you're going to find out that the V is cancelled, okay? I cancel this V, I cancel that V, cancel this V, I cancel that V, because what I'm doing on the numerator is exactly what I'm doing on the denominator, so nothing is going to change, okay? Right, so my answer, if you do your calculations there, your answer is going to be equal to 2.36. That's a numerical value for Kc. Okay. Now, if you look at the units, okay, units for concentration is moles per liter, moles per dm cubed. Okay, moles per dm cubed multiplied by moles per dm cubed over moles per dm cubed multiplied by moles per dm cubed. That will cancel. Okay, so our Kc has no unit at all. Okay, so this is how you could work out the question that came in November 2002, paper 2. What is important here, students, is for you to know number of moles initially present, okay, and then number of moles at equilibrium, concentration at equilibrium. Once you have those 3 lines, then you are in a position to calculate Kc. Okay, remember, if they bring masses, you have to convert that to number of moles, because this deals with concentration, and concentration is better when you have number of moles and a volume that is given. So this was the expected solution. That was for question 2C, November 2002, paper 2. Thank you.